Hello, and welcome to Team 13's EGB320 project for 2021. We have been tasked by EGB320 to design and build a prototype rover to find and collect samples of a specific colour on the Moon. This resulted in the creation of our Moon Access and Resource Collection rover, affectionately known as Mark Rover. My name is Eli Holzberger, and I was given the task of designing and building our mobility system and PCBs. We're using a differential drive system relying on two motors with lightweight rubber-clad wheels at the rear and acrylic roller wheels at the front for stability, as these are cost-effective and have good ground clearance, ensuring ease of access to the lander ramps. The rover uses 298:1 ratio micro-metal gear motors, which provide more than enough torque and excellent motor control, even at slow speeds. These are controlled through a bidirectional motor controller via a custom PCB which regulates and supplies power to the brain of the robot, a Raspberry Pi, as well as the sample collection servo and motors. These are controlled via pulse width modulation, ensuring precise speed adjustments to each motor as the robot goes about its work.
For the subsystem sample management, 4 requirements were set out at the beginning of the semester. These were to hold 2 or more balls, hold them all 1 centimeter above the mat, collect with an accuracy of 50 millimeters either way, and be powered by 2 or less motion components. The first design made was this pinwheel design with a guide to hold the balls in once they were collected. It could collect 3 balls, and a downside was that it was very big and it would barely fit in the 15 centimeter cube, and it didn't have a way of flipping rocks. The second design was modified, and it was a smaller version of the first design. It could collect the balls very well, and it was able to flip rocks, just not as successfully as we wished to. The final design chosen was this design here, which uses 2 arcs. So it uses a bigger arc and a smaller arc, and this allows for 2 balls to sit on it. The first ball to be collected sits up the top, and then when it drives up the lander, it falls down. This system fit well onto the chassis, and there was plenty of room for PCBs.
Hello, my name is Joshua Spence, and I was given the task in creating a navigation system. With the code, we chose to use Python, as it was found to be the most powerful script to run on the Pi. It was also found that Python had the most pre-built libraries for our vision, making it easier if navigation was just built in Python, so we could easily communicate with Vision's code. For our navigation design of the robot, we chose to use a reactive type over such as a pre-planned / hard-coded robot. The reactive type of the robot had more advantages over other methods, as it meant we didn't have to see the field beforehand. This would allow us to make additions such as a state machine. With the use of said state machine, it makes it easier for the robot to be stopped and started, being able to easily read it and make slight adjustments at any time to the code to get what and where is desired.
The vision system requires us to identify the different key objects, and each object identifiable by using certain color. In this, we use XC3 colors because XC3 colors are much more robust to a change in external lighting compared to RGB colors by. Isolating the key object, we use the thresholding method over the KNX method because thresholding requires less processing time and result than the KNX method, but it requires more steps of microprocessing to remove the noise and calibrating. To calculate the range and bearing, I use this following method. And here are some images of how the vision subsystem works in real life.